Hello, boys and girls. So you might not know this about me, but I'm deeply in love with the geometric series, and the geometric sum I also like a lot. You see the geometric sum here, right? So if you have the sum over all k over these monomials a to the power of k, then all these sums actually join together, and you get this simple fraction a to the power of n plus 1, so one more than the index here, minus 1 divided by a minus 1. And of course, if you go with n to infinity and this term goes against 0, then you get the famous geometric series. Okay, and I was walking yesterday and I was thinking, something I don't like too much about it is these monomials a to the power of k. What is actually the formula where these are all, like, it's a product not of k's but different terms, and so I thought about it, and it was actually surprisingly simple even to do in my head, and I will present you this theorem in this video. So the ingredients that we need, something that is sort of not there in the simple geometric sum case, is that we have a ratio of these expressions h minus and then the unit. We will work in a unitary ring where these h's can be different expressions in some finite sequence, and we have this ratio of 2 of these h minus 1, and then we have this product, the normal product over the h's from 1 till some k which is smaller than n. Okay, and in the case that all these h's are the same term, like for example if all hj's are the term a, then this product here will be the a to the k, and this is how this reduces to the known formula. And so the theorem I have here written down here, the sum over these products, this is basically the sum over all a to the k in the special case, and then this expression, this ratio, if all these h's are the same, then this is actually 1, so this term is new here, this factor is new, equals, and then this expression which you also know, like this is basically a to the power of k minus 1 divided by a minus 1. We could also write 1 minus the product divided by 1 minus this term. Okay, so this is the theorem, and we're going to prove it. Maybe I was thinking maybe it's natural to bring all this, get rid of all these negative signs and bring everything on the other side, and see this sort of as a formula of taking this general product and breaking it apart into summands terms. There are several of these formulas. I have used them before in research and this kind of stuff. So these are always nice in my view. And so here I give another way of reading the same theorem, just redefining these terms a little bit. But okay, before I go into the proof of this new theorem, I just want to point out that the geometric sum formula, there's like a slight generalization. It's like the generalization can immediately be proven from the non-generalized version, but it's still nice to look at. So I define here this sum u like so. This is the same sum as before, except we have a new factor b here. If b is 1, then we have just again the sum that we had before. And this also can be turned into this simple expression there. Again, if you plug in b equals 1, b equals the unit of the ring, then this is what we had before, but this is a little bit more general. And here you can pause the video to see why it should make sense that here you also have this sort of cancellation that we will see in the proof in a second, why this actually works out. But okay, I just wanted to point this out because this is almost equally as nice to write down as the geometric sum, but it's a little bit more general. Okay, so the proof is also very short. That's why I managed to do it in my head basically. We start, like what I will do is I will not jump immediately to the unitary ring with all the inverses and so on, but I will do it basically step by step. That's actually how I got there. So first we just work in a group, right? We have some product, and we have inverses for all elements in this group. And so if you have this sequence can even be an infinite sequence, whatever, like a sequence of these group elements. Then if you pairwise write them down, you know, gk plus 1, and the second term is like inverted, even if it's a non-commutative group, like not an abelian group. If you do the product over those expressions, then you have like this pairwise telescoping cancellation. And so this product over this sequence written down like this is actually just the first term, and then the last term wherever you stop term n to the power of -1, right? So you have this cancellation, and this is the cancellation how the proof in the end works, even if you're just here in the group context. For the abelian group, right, you don't write multiplication, but you write like plus, and then this expression which we have here, this product, is just this sum. I switched, you know, this product becomes the sum. Here's this simple expression we have like this. This is like just a telescoping, very generic telescoping sum. And then we consider the elements to be a product. Like, you know, for example, gk is the product of another sequence hj from 0 here, even from 0 to k, right? So we now pass on from this simple terms g to introducing another product, which is now, you know, now I'm not. Okay, I hope this doesn't confuse people. So here I use the product over the group, which then, you know, I've written it down in generality, but then I actually talk about the sum. So this product became the sum, and now I'm going into the ring, like for example in the reals. I have another product because, you know, my product became the sum, and now I have another algebraic operation, which is the product in the ring, which I denote by this normal product sign. All the elements are these products. And now if I take just this expression, which I've just, you know, demonstrated, the thing looks on the left hand side like this. There's this product minus the unit. Okay, I divide out the h0. So, you know, I take this expression, plug in the product, divide out the first term so that the unit appears here. And then, because I used a product here, and this term gk plus 1 has one more factor than this product here, I can pull out this last factor and rewrite it like this. And then basically if I divide by any number here, then I already have the theorem that we started with. So if I divide this by hi plus 1 minus e, just, you know, to make it look more like the geometric sum, then we have the theorem. And just for you to, you know, buy into the formula, like how this always works out. Like let's say, for example, we just choose n equals 2, and we look at this sum of products. I bring this e on this one side, and then I look at this the first one. Plug in n equals 2. The first term is k equals 0. So h1 minus e, and then the empty product. So this is exactly this expression, and then the second term, and so on and so forth. And then if we you know write it down, look at all the terms, then we see we have this perfect cancellation. This e cancels with this e, h1 times e is h1, and this is cancelled with this term, and so on and so forth. And in this sum, by telescoping, only always this last term survives, which is like the product of these h's, and so this gives exactly this kind of thing on this side. Okay. So I hope you like this little formula. I scroll up again. I don't know if this is of any use. I might eventually, you know, check out if I can use this sort of expression with some operators, because, you know, I've proven it in this ring generality. Give me any sort of operator space, and these tend to be rings, and so that might be of some use. I don't know. I'm always on the look for like this sort of relations that I can use with proving new silly theorems. So I can stay under 10 minutes, which I love. I hope you like that, and I wish you a pleasant night. Sleep tight.